So welcome to the next section of the multiple choice. So as we start with the multiple choice, question number 21. So the wave number of shortest wavelength transition in Balmer series of an atomic hydrogen will be. Now over here they have given us a hint that it is a Balmer series. So when there is a Balmer series, we know that N1 is going to be as 2. So this is not a problem for us with respect to the Balmer series. Okay, but now there are two different conditions. Sometimes you will get over here as shortest wavelength, okay, or the higher energy. Sometimes you would get it as the longest wavelength. Okay, there are two possible questions. Now, whenever there is a short or the shortest wavelength given, okay. So in this particular condition, what we have to understand is, if we consider this point as a point of the nucleus, this is the shell number 1, shell number 2, shell number 3, 4, so on and so forth. Let's say this is an infinity. Okay, so now here the electron is going to be de-excited from an infinite number of shell to particularly the shell number 2 in this particular case. Because whenever the electrons are de-excited to n is equal to 2, we are going to get the Balmer series, right? So when the de-excitation occurs, the extra energy that is going to be given out, this particular energy that is given out is in the form of the radiation. Okay, and this radiation is going to have the shortest wavelength, or I can say as a higher frequency. Okay, so therefore, what hint that we get over here is the N2 is equal to the infinity. So as we solve this one, we would like to take into consideration of nu bar is equal to 1 over lambda is equal to RH into 1 over N1 square minus 1 over N2 square. This is a formula which is required for the hydrogen. Okay, as Z is equal to 1, I have not included over here as the Z concept here. Okay, so therefore, when we use this formula, okay, so what we have is RH. RH value we already know 109678 per centimeters, right? So N1, what we have is a Balmer series, so N1 is 2, and N2 is coming from an infinite shell, so infinity, right? So when we have it, nu bar is equal to 109678 into 1 over N1 square. N1 is 2, so directly I will write it over here as 1 over 4 minus 1 over infinity square is nothing more than 0. So we'll take it over here. Nu bar is equal to 109678 divided by 4. We will get over here as 27419.5. Okay, but what they are expecting us is the shortest wavelength. They are expecting a shortest wavelength. Over here we have taken a nu bar wave number. Okay, so therefore wavelength is nothing more than 1 over nu bar, and that is equal to 1 over 27,419.5. When we try to solve this, we would get an answer over here as nearly equal to 0.003647. Okay, so meters. Therefore, this can be also written in the form of the angstrom units, because we have all the things over here in the form of the angstroms. So therefore, if we try to write it down in the form of angstroms, we would get it over here as 3647 angstrom units. Okay, so this is the answer. So let's observe. So first one is 4215 angstroms, which is not correct. Second one, 1437 angstrom. No. Third, 3942 angstroms. No. So fourth option, that is 3647 angstrom. So the answer for question number 21 is D. Okay. Moving towards the second question, that is the question number 22. the number of spectral lines obtained when an electron jumps from the fifth excited state to the third excited state. The number of spectral lines obtained are, okay. So here, if we observe the number of spectral lines, alright, so what we have is N, 2 is 5, N, 1 is 3. This is what we have, right? So therefore, so when we solve this, you should keep in your mind about one formula. The formula is N2 minus of N1 into N2 minus of N1 plus 1, the whole thing divided by 2. Okay, so for the understanding the transitions that are going to occur from two different states over here, this is a formula what we usually take. Okay, so now substituting the things in this particular formula, 5 minus of 3 into 5 minus of 3 plus 1 divided by 2. So that is going to be 2 into 5 minus of 3 is going to be 2, 2 plus 1, 3, 3 divided by 2. So the answer is 3. Right? So 22. So if you want to understand this, let's say that n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, n is equal to 6. Now, these are the different energy levels, let's say. So now what they are saying is the electron jumps from the fifth excited state to the third excited state. So this is one transition. This is the first transition what we already know. This is a one possibility. Second possibility is that from the fifth the electron can come to the n is equal to 4. This is the second possibility. Third possibility is that from the fourth it can come to the third one. So the total number of transition lines or the spectral lines that we can have is 1, 2 and 3. Okay, so this is the answer for question number 22. Moving forward with question number 23. It says that the Bohr's radius for the hydrogen atom is approximately 0.53 angstroms. So they have given us the radius as 0.53 angstroms. Okay. So the radius of the first excited state N2. That means if you consider over here this as the nucleus. Okay. This is the first orbit or the first shell. Right? This is the second orbit or the second shell. But when an electron that is residing over here, okay, as you supply in the energy, what is going to happen is the electron is going to absorb that energy. As the electron absorbs that energy, this particular electron gets excited. It goes to the next orbit, right? So that time we consider this as the first excited state or the first excited orbit. Okay. You supply in the energy, again the electron jumps from the first excited state to the second excited state over here. But second excited state means it is a third shell. Okay, right now we are worried only about the second shell here. Okay, fine. So what they are asking is the radius of the first excited state, n equals to 2 of the orbit is. Alright, so we have a direct relationship. Rn is equal to 0.529 into n square. Okay, so some of them also take it as 0.53 into n square. You will come almost approximately the same answer. Okay, so therefore R2 over here equals to 0.529 into, okay, we require the second orbit. So therefore replacing the n is equal to 2, we are going to get over here 2 square. So therefore that is going to be 0.529 into 4. So when you multiply this, you will come across 2.119 angstroms approximately. So I can write this down as 2.12 angstroms. Okay, so the answer over here for the question number 23 is going to be option D in this case. So therefore, what we have is option D, that is 2.12 angstroms. Okay, so moving forward with the next one. So question number 24. The first emission line in the atomic spectrum of hydrogen in polymer series appears at. Okay, first emission line. So therefore, when they are speaking about the first emission line, and they have given as the polymer series, N1 is equal to 2. Okay, so for the first line, okay, let's consider these are the energy levels. N equals to 1, N equals to 2, N equals to 3, N equals to 4. Okay, so now Balmer series is a series obtained when the electrons are de-excited from their higher energy states to the N is equal to 2. This is what we already know, right? So now when the electron comes from N equals to 3 to N equal to 2, when this transition occurs, that is the transition which is going to give us the first emission line. Okay, so therefore, when we take this into consideration, what we have is N2 is equal to 3. So therefore, when we substitute it in RH into 1 over N1 square minus 1 over N2 square. Okay, substituting these values, we are going to have it as, see, they have given it in form of RH over here, R, that is nothing more than RH, the Rydberg's constant. Okay, you can keep it as R or RH. So do not substitute this value here. Okay, so therefore, let's keep it as it is R or RH. So N1 square, that is going to be 1 over 2 square, that is 4, minus 1 over 3 square, that is going to be 9. Okay, R. So therefore, so taking over here, we are going to take the LCM over here, that is going to be the 36 over here, 9 minus of 4, R in the bracket of 5 over 6. Okay, so if you observe this, it's going to be the answer as D. So we have that answer D over here, 5R by 36, so R into 5 over 36. So we get over here direct answer, but one thing that we have to understand is they have not substituted the value of the constant, so they are giving the direct answers over here. You substitute the answers, you will get much more precise ones. Okay, so going forward with the next question number 25. Which of the following species Bohr's theory is not applicable to? Okay, so Bohr's theory is applicable to those particular atoms or the species which are going to have a single electron systems. Okay, so in that particular case, it is not applicable to. Now here it is a hydrogen atom. They are taking over here hydrogen atom, one electron system, perfectly done. Okay, but if you observe He plus 2. So when we have He, okay, helium actually has 2 electron systems in it. But while taking in option number B, they have taken it as He plus 2. Plus 2 refers that the 2 electrons are being lost from the system. These 2 electrons are lost. Okay, so as a result of which, what is going to happen is, this has 0 number of electrons. No transitions will occur. So therefore, Bohr's theory is not going to be applicable to He plus 2. While if you see lithium has 3 electrons, but it is in a form of Li plus 2 state. Plus 2 in a sense, it has lost 2 electrons. Yet there is 1 electron there. Similar is the case with Be plus 3. Okay, there is 1 electron in that system too. So therefore, Bohr's theory is applicable to hydrogen, lithium plus 2, Be plus 3 over here. It is not applicable to He plus 2, that is a helium plus 2 state. Okay, so going forward with the next question. So Question number 26. What is the wavelength of radiation emitted producing a line in Lyman series when the electron falls from the fourth stationary state in the hydrogen atom? Okay, so they are saying that it is a Lyman series over here. Lyman series. Okay, so Lyman series is going to be obtained when an electron jumps from any of the higher orbits to n is equal to 1. Right? This is what the condition is. So therefore, they have said that n1 is equal to 1, n2 is equal to, it's coming right away from 4th. Okay, n2 is equal to 4. So therefore, if you observe this, so they are looking forward for the wavelength. Okay, fine. Wave number is equal to R value, they have given it as 1.1 into 10 raised to 7, right? Orbitals. Okay, fine. So divided by 1 over n1 square minus 1 over 4, that is going to be 16 in this case. So therefore, 1 into 10 raised to 7, 15 over 16. So 15 divided by 16, you are going to get it as 1.1 into 10 raised to 7 into 0.93 approximately. Okay, this is for bar. Alright, so nu bar is equal to so nu bar is equal to 1.023 into 10 raised to 7. Okay, therefore lambda is equal to 1 over nu bar, that is equal to 1 over 1.023 into 10 raised to 7, and that is going to be, when you take this 10 raised to 7 on the numerator, you are going to get it around minus 7 meters over here. So therefore, let's see. So 1 divided by 1.023 is going to be approximately equal to, which is approximately equal to 0.967. Okay, 0.96. So you can take it over here. So 0.96. So when we shift this particular decimal to 2 digits, so 96.7 into 10 raised to minus 9 meters. So that is going to be as a nanometer in this case. So 96 nanometers should be the correct answer, and that is nothing more than option A in this case. Okay, so going forward with the next question, number 27. In hydrogen atom, the energy of the first excited state is minus 3.4 electron volts. Okay. Find out the kinetic energy of the same orbit of hydrogen atom. Okay, fine. So they are saying that the electron is present in the same orbit. So remember that the kinetic energy is equal to the total energy of electron which is present, which is equal to the same one. That is nothing more than 3.4 electron volt. Okay, so therefore you are going to see that answer as 3.4 electron volts. Is the correct answer for this, and that is the option A. Okay, so answer is 3.4 electron volt, option number 8. Next one, in Bohr series of lines of hydrogen spectrum, the third line from the red end corresponds to which of the following inter-orbit jump of electron for the Bohr orbit in the atom of the hydrogen? Oh, okay. In order to understand the question such as the question number 28 in this particular case, first, they are saying that we are going to have the third line from the red end. Now, red end, when they are speaking about the red over here, we have to understand that It is from the Balmer series. Now why it is from the Balmer series is because you can actually see the radiation. And the Balmer series is only one series in the hydrogen spectra which falls in the visible section. Right? So now, Balmer series, Lyman-Balmer, therefore n is equal to 2. Okay, so now here, if you observe, they are giving you another hint, the third line from the red end. The third line from the red end. That means, as you see the entire spectra, in the visible spectra, okay. So what will happen is, as we go towards the red color section, okay, from the violet to the red, okay, as you go here, as you come to the red end of the spectra, here energy goes on decreasing. I repeat again, here the energy of that particular radiation goes on decreasing while the wavelength increases. So here, in this case, whatever radiation you are getting, the radiation is of the lower energy. The lower energy is formed when an electron jumps from the smaller orbit, that is, if it is n equals to 2, okay, this is, let's say n is equal to 2, okay, let's say this is n equals to 3, let's say this is n equals to 4, this is n equals to 5, so on and so forth. Okay, so now, when an electron jumps from 3 to 2, 4 to 2, 5 to 2, whatever the radiations we are getting, these radiations have the smaller amount of energy, or you can say as a greater wavelength. Okay, so as we go far away, okay, as it goes almost to the infinity, what will happen here is when the electron jumps from a very bigger orbit or a very farther orbit to the n is equal to 2, that time the radiation what comes out, that radiation is going to have a huge amount of energy in it, but lesser wavelength. Okay, so applying the same concept here, you can neglect 4 to 1, 2 to 5 because they are speaking about the Balmer series. So Balmer series is formed when the de-excitation takes place from a higher orbit to the n is equal to 2, right? So taking that into thought, taking that into consideration, these two can be nullified out. So what remains with us is 5 to 2, 13 to 2. As I said, when an electron comes from the nearby orbit, the radiation which comes out, that radiation is going to have the lower energy or the higher wavelength. Okay, so as it is coming almost near from the red region, okay, it should be 5 to 2 transition. It cannot be a 13 to 2 transition because if that particular electron is coming from the n is equal to 13 to n equals to 2. That time whatever energy comes out, that energy of radiation corresponds to the higher frequency. That will be nearby the violet section. Okay, so this is the explanation for question number 28. So the answer for question number 28 is A, that is 5 to 2. Moving forward with the next question, that is the question number 29. So question number 29, the wavelength of radiation emitted when in a hydrogen atom the electron falls from the infinity to the stationary state, what would it be? Okay. Quite easy, quite straightforward answer over here. So what do we have? RH into 1 over n1 square minus 1 over n2 square. Okay, so first one, what we have is n1 is equal to 1, n2 is equal to infinity. This is what we already know. Okay, so substituting these particular things, our value is 1.097 into 10 raised to 7 over here. So 1 over 1 square minus over here 1 over infinity square. Already know that this particular value is going to be 0. So what we have is this particular value here. So nu bar is equal to 1.097 into 10 raised to 7. So what I require is the wavelength. Are they asking for wavelength? Yes. So therefore, wavelength is equal to 1 over 1.097 into 10 raised to 7. So 297. So lambda is equal to what we get over here is 0.911. Okay, into 10 raised to minus 7. So lambda is equal to, we can go with as shifting this to 2 digits. So 91.1 into 10 raised to minus 9 meters. So this is nothing more than the nanometer. So therefore, what we have is lambda is equal to 91.1 nanometer. This should be the answer. So therefore, question number 29, answer is C, 91 nanometers. Right? What with the next one? Okay. Question number 30. The most energetic transition of electrons in hydrogen spectra are formed in. Where are you going to find it? Okay. Now, the most energetic transition. Now, when it is formed, when the electrons are going to be de-excited from the higher energy levels, to n equals to 1. Anything that falls from the higher energy level to n equals to 1, that time the radiations which are going to be emitted out. These radiations are going to have the higher frequency, or I would say it as the lower wavelength. In short, it is going to have a good amount of energy. The most, you can say, as energetic transitions of them. So therefore, that particular thing, any transition n is equal to 1, that is a Lyman series. So therefore, the answer for 30 is going to be the Lyman series. Okay. Second possible explanation also you can give that is the energy that is about these radiations, or the radiations that are going to be emitted here. These radiations are visible in the ultraviolet region. As we come to Palmer series, these particular radiations are placed in the visible section. Next one, Passion and bracket, we get these particular radiations in the ultraviolet region. While the Passion and bracket, these particular series, we get them in infrared section, right? So therefore, as these are obtained in infrared, Balmer series is obtained in visible, Lyman series are obtained in the ultraviolet. Because they are obtained in the ultraviolet, these particular radiations have a good amount of energy, higher amount of energy. Okay, so therefore, it is considered as the most energetic transition of electrons. In any subshell, the maximum number of electrons having the same value of the spin quantum number is, okay, so when we speak about the subshells, okay, so subshell, so here, let us say we have the p subshell. So in the p subshell, we have the 3 orbitals over here, pxy, py, sorry, we have 3 orbitals, that is px, py and pz, right? So therefore, in order to calculate how many number of electrons are going to have the same spins in this case, we apply the particular formula 2l plus 1. Okay, where L is the azimuthal quantum number. So L for P, we already know the value as 1. So applying this case, so 2 into 1, we get 2, 2 plus 1, 3, right? So therefore there are 3 electrons with similar spins in this case. Maximum number of electrons with same spin can be 3. You can apply for the d orbitals also. So for the d orbitals, what we have the value as for azimuthal quantum number, it becomes as 2. So for d orbital, so 2 into 2 plus 1, that is going to be 5 electrons, right? So when we take a look into the d orbitals, okay, 1, 2, 3, 4, 5. So for the d orbitals, what we are going to have? 1, 2, 3, 4, 5. Maximum 5 electrons having the same spin. So you can apply this formula, that is 2l plus 1, in order to understand how many number of electrons in a particular subshell can have same spins. Okay, so the answer for question number 31 is C, 2L plus 1. The next one, that is question number 32. For principal quantum number n is equal to 4, the total number of orbital having L is equal to 3. So, principal quantum number is 4, L is equal to 3. Okay, for 3, remember L is nothing more than azimuthal quantum number. So, L for S is 0, for P is 1, for D is 2, for F it's 3. Right? Now, when we speak about the F subshell, this F subshell has 7 orbitals in it. So, as it has 7 orbitals, okay, now here the total number of orbitals having L is equal to 3, L is equal to 3, we have 7 orbitals. If they had said it as L equals to 2, it would have gone for D subshell. D subshell has 5 orbitals. L equals to 1, P subshell will have 3 orbitals, right? So that is how it all goes. So what we have here is for 32, answer is B. Okay, so we have 7 orbitals. Going forward with the next one, that is question number 33. For azimuthal quantum number, L is equal to 2. The maximum number of electrons will be. So, L is equal to 2. Okay, L is equal to 2. We already have taken the values. So, L is equal to 2. That means it is going to be the D orbital. Okay, or D subshell. So, we have 5 D orbitals over here. So what are the 5 D orbitals that we have? 1, 2, 3, 4 and 5. So we have dxy, dyz, dzx, dx squared, y squared, and finally one is a dz squared, right? So we know that every single orbital has a capacity of filling 2 electrons. So 2 into 5 becomes as 10. So L is equal to 2 for D subshell. It can have 5 D orbitals. 5 D orbitals, each one of it can occupy 2 electrons. So total number of electrons in L is equal to 2 will become as 10. So answer over here will be the 10 electrons can be filled up in these orbitals. Right? So going forward with the next question, question number 34. Going forward with question number 34 here. Which of the following atomic orbital does not have the 4 lobes symmetrically between the axial directions? Now axial directions over here are nothing more than these. So let's say x-axis, y-axis, z-axis. Okay, so now there is only one particular orbital in D subshell which is not lying in between. It is not lying like this in between these x and y and z. It is lying exactly on these particular axes. And that particular one orbital is going to be represented something like this. Okay, so this is that particular orbital which has the lobes exactly on the axis. So that particular thing is nothing more than dx squared y square. This is the only orbital in the d subshell which is aligned perfectly on the axis. So therefore, let's check whether we have that answer over here. Yes, that is the option C, d x square y square. With respect to the third shell they have taken into consideration. So 3dx square y square. Okay. So question number 35. The number of nodal planes for 4d orbital is. Okay. So nodal planes. Remember here, nodal plane is also called as angular node. Is also called as the angular node. Okay. So angular node for any orbital is always equal to L. L is nothing more than the azimuthal quantum number. Okay, so for what they are speaking, first we'll observe for 4d orbital. Okay, so they are speaking for 4d orbital. So for 4d orbital, value of L will be equal to 2, right? So therefore, taking this particular expression, if you observe this expression, therefore, angular node or what we have, nodal plane is equal to 2. Okay, do we have the answer here? Yes, C, that is 2. So, nodes, nodal plane, nodal point, nodal region. Okay, these are nothing more than the points or the region or the surface where the probability of finding the electron will be 0. Correct? So therefore, that was about the node. A new electron enters into the orbital when the value of option A, n plus L is maximum, option B, n plus L is minimum, option C, n plus M is minimum, option D, n plus M is maximum. So now, in this case, try to remember n plus L rule. Okay, so whenever the electron enters into the orbital, this value, that is n plus L value, should be minimum. It should be minimum, right? Then only the electron enters into that specific orbit. Coming forward with the next question. If the radius of the first Bohr orbit is x, okay, let's solve this. Question number 37. Okay, the radius is given as x. Radius is equal to x, right? So, now taking into consideration of the formula, that is the radius of orbit can be given as r into n square, where n will represent to us which orbit are we speaking about. Alright, so therefore, if we are speaking about the third orbit, for the third orbit radius, okay, the radius in this particular case will be equal to r into 3 square, that is nothing more than 9r. But the radius is given as x, so therefore can we write it down as 9x here. Okay, so what we have in the first one is the 9x. So taking into consideration of the angular momentum, okay, in consideration of the angular momentum, can we write it down as m into v into r is equal to n into h over 2 pi. Okay, where n is equal to 3 because we are speaking with respect to the third orbit in this case. Therefore, when we write this down, let's replace r as 9x. So m into v into 9x is equal to n is 3 into h over 2 pi. So as we can get an de Broglie's expression as H over m bar v. That is shifting the momentum to the denominator over here. So as we shift this m into v to the denominator, we can take this 2 power on the other hand. So 9x into 2 power divided by 3. Right? So therefore, what we are going to have? 3 ones, 3 thrice is over here. So 3 into 2 is going to be 6. So therefore, that is going to be 6x pi. So the answer is B, 6 pi. The next question, that is the question number 38. If the Planck constant H is 6.6 into 10 raised to minus 34, okay, joules, then the de Broglie wavelength for a particle having the momentum. Now, momentum is nothing more than m into v. Okay, m into v. So here is 3.3 into 10 raised to minus 24 kg per kg meter per second. Okay, will be. Okay. So the de Broglie wavelength is given by lambda is equal to h over m into v. Okay. So therefore h 6.6 into 10 raised to minus 34 as what they have given to us divided by m into v. That is the momentum. So therefore momentum is 3.3 into 10 raised to minus 24. So once, almost twice. Okay, so quite simple one. 2 into 10 raised to minus 34 goes on to the top over here plus 24. So therefore minus 10 will be the answer. Meters, and that is nothing more than the angstroms. So therefore, what we have is the answer C in this case. Right? Moving forward. Question number 39. Question number 39. The ground state electronic configuration of Fe plus 3 state. Now they have given us Fe plus 3 state. First, we shall understand Fe. Okay, atomic number over here, atomic number, what we have is 26. So, therefore, taking the electronic configuration into consideration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, let's check, 10, 11, 12, 12, 18, 19, 20, this is 6. Okay, so they have taken Fe in the form of Fe plus 3. That means it is going to lose 3 electrons. Always remember, the 3 electrons are lost in the manner as 2 electrons for the outermost shell, that is for the 4 in this case with S equals to 2. Okay, so 2 electrons for 4s and 1 electron we are going to lose it from 3d. So therefore, as we lose it, this thing will become as 4s0. This one will become as 3d5. The rest thing remains same. I can write down this as the argon electron configuration. Okay, so therefore, the option over here which suits this answer is going to be C. Right? So C is the answer for this. Now, if you observe the question number 40 is almost the same one. What they have asked is the number of unpaired electrons in Fe plus 3 state. Okay, again, you need to remove the electrons and we need to understand that this is a d orbital over here, 3d orbital. So in this case, how many number of electrons are there? Because this is the outermost now. Okay, how many number of electrons are there which are unpaired? So when we take this, 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay. So for the d orbital, that is for 3d, for Fe plus 3, there are 5 electrons. Let's fill them 1, 2, 3, 4, 5. Right? So there are 5 unpaired electrons in Fe plus 3. But if it was a simple Fe, then what would have happened? It would have got an electronic configuration as 3d6. That means 5 electrons and then pairing starts, one more electron over here. It would be for an Fe. Okay, so that time we would have as 1, 2, 3 and 4 unpaired electrons. Right now, for Fe plus 3 condition, we have the 5 unpaired electrons, right? So therefore, for the question number 40, we have the answer over here as C equals to 5. So we have completed another set of questions. We'll see you in next video.